This video, we're going to talk about implicit differentiation and related rates. They're connected topics, two different sections in your textbook, but we're going to talk about them at the same time since they're so closely related. So first objective here, we're going to find derivatives using implicit differentiation. Then we're going to find second derivatives using implicit differentiation. Then we're going to use implicit differentiation to find slopes of curves at given points. We're going to use implicit differentiation alone with product, quotient, and chain rules to find derivatives of functions. Then we'll solve applications involving related rates, and we'll solve related rate problems using geometry if time permits. Actually, we'll definitely do one of those because we'll have a Pythagorean theorem problem that we're going to do. That'll be one of our geometry applications. So let's go ahead and talk for a second about what we mean when we say implicit versus explicit. So recall the definition of a function: y equals f of x, where y is our dependent variable and x is our independent variable. And for each x, there's going to only be one y. And when we set it up this way, we get all of our dependent variables on the dependent variable y all by itself, separated from all the independent variables and constants on the other side of the equation. And this is going to be an explicit definition. So there is exactly one value of y for each value of x. Now we're going to have some other relations and things like that that are not that way. We're going to have other functions that are going to be defined that aren't going to be able to be defined explicitly. So, but this is an explicitly defined function of x called f, which defines y. You can think about a circle though, right? A circle is not going, y is not going to be a function of x. It won't pass the vertical line test. If we draw a circle here, y is not a function of x, but there's a relationship between x and y that x squared plus y squared equals r squared. So can we write this expression as an explicitly defined function of x or even y? Let's try it. I'm going to tell you we're not going to get just one piece if we try and do that. So we can try to say y squared is equal to r squared minus x squared. And then y is equal to plus or minus the square root of r squared minus x squared. If we tried it the other way, x squared is equal to r squared minus y squared, and x is going to be equal to plus or minus the square root of r squared minus y squared. So we can either get the top half and bottom half of the circle separately as y as a function of x, or we can get right half and left half separately with x being a function of y. But we can't get both halves together as functions either of x or y. So these are functions here, this positive part and this negative part. And I'm going to do the top part here in blue. I'm going to label that y equals root 1 minus x squared. We're going to let r equal 1 here. This is going to be our unit circle that we're talking about here when r equals 1. And this bottom half here, I'm going to make blue and green are too close together. Let's make it red. Like that. y equals negative root 1 minus x squared, like that. And so we can do this sometimes, but not every time, where we can split it up into two explicit functions like that. But now we've just doubled our work to try and find the slope of the general slope function. We have to find it in two pieces. We have to find an equation for the blue piece, and we have to find an equation for the red piece, and they're going to be different. So let's go ahead and let's see if there's a way to do it all together and save ourselves from doubling our work. Let me get back to my blue pen here. So first question, can we always come to this conclusion? Is it always possible to write two or more explicit functions like this? No. For example, we could have something like y squared ln of y plus ln of x is equal to x squared plus 2x minus 9. And can we solve for x? And could we solve for y? Can't really solve for x, because if I got the x's together on one side, like I can't get this equal to 0 over here to use the quadratic formula, and I still got this ln piece here going on with that. And then I've got a whole lot of other mess going on. I can't get the y's away from each other. I could use some properties to try and maneuver some stuff around, but I'm still going to end up with x's and y's together, and I can't separate them. So no, it's not always possible to get an explicit definition. So sometimes we're going to have to do what we call implicit differentiation. So let's use those explicit functions that we just found for the unit circle. Y equals square root of 1 minus x squared. Let's take the derivative of this by using our power rule with our chain rule. So 1 minus x squared to the 1/2 power. Y prime is going to be 1/2, 1 minus x squared to the negative 1/2 power times a negative 2x when we take the derivative of the inside. Half of negative 2 is negative 1. Y prime is going to be a negative 1 over the square root of 1 minus x squared. Now, if we were going to take the other piece over there that we drew in red, do a very good job with my equal sign. Let me fix that. Y equals. Now we have y equals a negative root 1 minus x squared, which is a negative 1 minus x squared to the 1/2. So y prime will be a negative 1/2, 1 minus x squared to the negative 1/2 times a negative 2x. Negative 1/2 times a negative 2 is a positive 1. So y prime is 1 over root 1 minus x squared, like that. And we get two different pieces there. This is the top half, this is the bottom half. And we've done double the work. Option 2 is to use implicit differentiation. So how are we going to do that? Well, we're going to differentiate each side of the equation. So we're going to take dy or d dx of x squared plus y squared is equal to d dx of 1. So we're going to do d dx of x squared plus d dx of y squared. It's going to be this term with y's in it. It's going to be interesting to us. We know that right-hand side is 0. the derivative with respect to x of x squared. That's pretty basic. That's 2x. Now we're going to use the chain rule because we have an outer squaring function and we have an inner function y that has x's hidden inside of it. We just don't see those x's. It's hidden behind the letter y. So we're going to use implicit differentiation here. We're going to differentiate the outer function in terms of y, and then we're going to multiply by the derivative of the inner function with respect to x. So that's going to be dy dx or y prime. Then we're going to solve for y prime. So 2y y prime is equal to negative 2x. Y prime is going to be a negative x over y. Always, all the time. That's what it is. Notice that your y in this case was a negative root 1 plus square root of x. So we'd have to put the negative in there to replace y. So that is a negative 1 over y there. And in this case here, this is, in both of these cases, I missed my x. So that is an x there, and that is an x there. The x's come from here and here. All right. So we would get negative x over y here. We would get negative x over y here. It's the same thing. So treat y as a function of x and differentiate implicitly would be what we would be told to do. So this is the idea here of there are x's hiding inside of the letter y. Even if I don't tell you there are x's hiding inside of the letter y, assume there are x's hiding inside of the letter y unless I tell you otherwise. And assume that for any variable that you see that you're told to differentiate with respect to another variable that you can't see, assume that that variable you're differentiating with respect to is hiding inside of that other variable, and that it's an implicit function. So we'll get to that more with related rates when we differentiate with respect to time, and we don't see time anywhere in the problem, but we have to stick these differentials on the end. What I wrote here as y prime, lots of times later we're going to be writing explicitly as dy, or not explicitly, but we're going to be writing more formally as dy dx, so that I see that I'm taking the derivative of y with respect to x. I'm going to have to use this form of the differential instead of this note. I'm going to have to use this notation here instead of that notation, because I'm going to have to tell people what variable I was differentiating with respect to. All right, so let's talk more about what happened. So what happened in the above example to the second term of the equation, which contained the y. Let's just do another example and see if you can see the pattern that anytime that we're differentiating a term that has a y in it, we're going to need to have a dy dx on the end. I'm going to start putting dy dx's instead of y primes, just so you can see. So option 1 here, let's go back. If we have option 1, we can split this into 2 pieces. Y equals plus or minus the square root of x. So y1 is going to be positive square root of x. Y2 is going to be negative root x. And I can differentiate this. dy1 dx is 1 over 2 root x. And dy2 over dx is a negative 1 over 2 root x, like that. Those are options 1 and 2. Or option 2 is to differentiate implicitly, and I like that better in this case. So differentiate the left-hand side with respect to x. So first we're going to differentiate with respect to y, and then we're going to differentiate y with respect to x. We only need to differentiate with respect to x on the right-hand side, but now I'm going to solve for dy dx. That's going to be 1 over 2y. And again, if I had solved for y in each of these cases, then it would make sense in y1 that this would be 1 over 2 times the square root of x. This one would be 1 over 2 times negative root x, and that negative would come up front. So we got the same answers both ways. If y equals square root of x, we get dy dx is equal to 1 over 2 root x. If y equals negative root x, we get dy dx equals negative 1 over 2 root x, which are the same answers. All right, so just as a little bit of an aside here, I mentioned this, when I take the derivative with respect to x of y squared, we're treating this like we're differentiating with respect to y first and using that power rule. And then we need to attach a dy dx or a y prime onto the end of it, because this is like a derivative with respect to x of f of g of x, where we have f prime of g of x times g prime of x, or you might say derivative with respect to x of f of u, which was f prime of u times u prime, something like that. This is the chain rule. We also can write the chain rule as df dy, if this is f right here, times dy dx will give me df dx. That's the other thing that's going on, is we're going through y to get to x. I don't know how to differentiate this exactly with respect to x, so I'm doing it implicitly and going through the variable y that I see to get there. So just another quick example here, d dx of x squared plus 4 quantity squared, like that. We can do this with the chain rule to say that this is 2 times the thing that's in parentheses times the derivative of the thing that's in parentheses, which would be 4x times x squared plus 4 would be 4x cubed plus 16x. If I expanded all that to try and do this without using the chain rule, this would be x to the 4th plus 8x squared plus 16. And that would be 4x to the 3rd plus 16x as well. Answers match. So just as a reminder, but the chain rule here, what's happening is that this function right here is getting hidden behind the letter y, and I don't know what it is to multiply by the derivative of it at the end. All I can do is stick a y prime or a dy dx on the end for the sake of the chain rule. So implicit differentiation just uses the chain rule. That's all that's going on. So let's go ahead and you can see that there's a chain rule happening behind the scenes. This can happen with all the rules. So now let's look back again at that unit circle. And though we've already done this, we're going to do it again. Derivative with respect to x of x squared plus y squared is equal to derivative with respect to x of 1. And we've got the 2x part taken care of. That was pretty basic. Now we've got the 2y, and we need the dy dx because we're implicitly differentiating. That's going to be equal to 0. The derivative of the constant on that side is 0. Now we're going to solve for dy dx. Using dy dx on purpose here, I used y prime before because I want you to get ready for related rates that are coming, and I want you to see things written this way. So dy dx is equal to negative 2x over 2y. So dy dx is equal to a negative x over y. Always, all the time. We saw that before. So if I have something like y is a g of x, and I take the derivative with respect to x of y squared, that's the same thing as saying the derivative with respect to x of g of x squared, like that, was 2 times g of x times g prime of x with the chain rule. That's the same thing as what's going on here. I'm just not using this prime notation anymore because then it gets confusing when you get to related rates. So a chain rule is occurring when we take the derivative with respect to x of y squared, and we get this extra y prime piece on the end. All right, we've talked enough about that function. Let's move on to some other functions here, and let's talk about what happens with x, y equals 2 and find y prime. So we've got a couple options here. Option 1 is, well, they told us to do it implicitly. So I'm just going to show you option 1, which would be an explicit definition to show you what we should get. But this is kind of aside. Over here would be option 1, even though that's not what we were told to do. Would be to say y equals 2x to the negative first. So y prime would be a negative 2x to the negative second, or negative 2 over x squared. So this is our target that we're aiming for. We know that we should be getting that. So let's use the product rule. And the product rule on the left-hand side says the derivative with respect to x of u times v is equal to u prime v plus v prime u. So I'm going to let my u be equal to x and my v be equal to y. My u prime is going to be 1. My v prime I'm going to let be y prime since I'm already using prime notation in my rule. So u prime v, that's going to be y, plus v prime u, that's going to be xy prime, equals the derivative of the right-hand side is 0. Let's solve for y prime. So xy prime equals negative y prime equals negative y over x. Now, how are we going to show that this is the same thing as that? Well, we know that y can be written as 2 divided by x. So let's keep going. We should be able to get an explicit definition here, and we should do that when we can. Since y equals 2 over x, negative 2 over x divided by x is equal to negative 2 over x times 1 over x is equal to negative 2 over x squared. And look at that. Our answers match when we do explicit function definitions and implicit function definitions. We get the same derivative both ways, both times. So again, for most calculus teachers, even if they tell you to use implicit differentiation here, they want you to go back and make this substitution for y for an explicit definition that only contains x's and constants if you can do it. They're not going to tell you in the instructions in the problem to do that, but they want to see that. When you can give a derivative that's an explicit definition, do that. Implicit definitions are less preferable since you need both coordinates, x and y. Only do that when necessary. So let's use implicit differentiation here to find y prime. This is going to be an example of where I cannot get an explicit definition for y. And so I'm just going to be happy to leave my dy dx in terms of x and y. So let's go ahead. This first term here is going to be pretty basic. It's going to be 3x squared. We've talked about this next term several times. I'm going to go ahead and use dy dx's here. Then we're going to use a product rule here. And I'm going to say the derivative of negative x is a -1 times y plus, and then leave the first part alone and differentiate the second part. So I get dy dx when I differentiate y, and I get 0 on that side. So I'm going to get my dy dx terms by themselves on the left-hand side. That's 2y dy dx minus x dy dx. So these stay on the left. Going to subtract 3x squared from both sides. And I'm going to add y to both sides. And that will isolate my dy dx terms on the left-hand side, since dy dx is what I want to solve for. I'm going to factor dy dx out, since it's a common factor. And that'll leave me with 2y minus x times dy dx is equal to a -3x squared plus y. And then I'm going to divide both sides by 2y minus x, divide by 2y minus x, and dy dx is going to be equal to a -3x squared plus y over 2y minus x. And only thing that I'm probably going to do just to make it look nicer is, so that we don't lose track of that negative, I'm going to write that term second as subtraction so that you don't lose track of that negative sign, like that. And this will be my final answer over here. Actually write that on its own step. So dy dx is equal to y minus 3x squared over 2y minus x. Final answer. All right. Let's use implicit differentiation to find y prime. I'm going to say dy dx instead. Okay. So 2y dy dx plus, and then take the derivative of the first part, leaving the second part alone, plus derivative of the second part, leaving the first part alone, and the derivative of the constant is 0. Let's get the dy dx terms by themselves on the left. Factor out my dy dx. Gives me 2y plus 3x squared is a -6xy on this side. And dy dx is equal to -6xy over 2y plus 3x squared. No better place for that negative to go than where it is. But notice there's no y prime terms on the right-hand side. All of the dy dx or y prime terms were on the left, and we factored that out and solved for it. Okay, I'm going to show you two ways to solve this problem here. So method 1 method 2. So method 1, I'm going to just go ahead and use the chain rule. And it's going to be kind of messy because I have a product rule inside of a log, but my first function that I see is the log. So that tells me to do 1 over the inside of the log. Then I'm going to take the multiply times the derivative with respect to x of what's inside the log. That's going to be equal to 0 on the right-hand side. So 1 over x times y times, now I have a product rule. So 1 times y plus, and then x times dy dx is equal to 0. So y plus x dy dx all over xy is equal to 0. Well, if that's the case, then we know that the numerator had to be 0. We know neither x nor y can be 0 here because we can't divide by 0. But we already knew that from the domain here. So that means y plus x dy dx has to be 0 because the numerator has to be 0. And x dy dx equals a negative y, and dy dx is going to be a negative y over x. Now, I think that was the harder method. Let's remember some of our log properties from pre-calculus, and when I have a product inside of a log, I can split up those logs like so. And now I'm going to differentiate. And this is 1 over x plus 1 over y dy dx equals 0. So 1 over y times dy dx equals negative 1 over x, and dy dx is equal to a negative y over x, like that. Second method did not require as much work, but it did have one preliminary step there. We still used implicit differentiation here because this ln of y is something that required implicit differentiation, since we had y as a function of x that's inside of the ln function. So don't forget that you're allowed to use pre-calculus before you start jumping in and using your calculus. It makes your problem easier sometimes, actually lots of times. That's why we do pre-calculus first. Let's find the slope of the tangents to the graph of a circle with radius 3 this time. We're not talking about the unit circle anymore. Circle of radius 3 at square root of 5, 2, square root of negative 5, negative 2, and square root of 5, negative 2. All of those points are on the circle of radius 3. Check them out with this formula: x squared plus y squared equals r squared if you need to. That tells me that x squared plus y squared equals 3 squared, which is x squared plus y squared is equal to 9 is the circle that we're dealing with. Let's go ahead and differentiate implicitly here. So that's 2x plus 2y dy dx is equal to 0. 2y dy dx is equal to negative 2x. And dy dx is equal to negative 2x over 2y is equal to a negative x over y. Dy dx is negative x over y. So I'm going to have x, going to have y, and I want dy dx, which is given to me as negative x over y. So my xy ordered pairs were root 5, 2. And then it was negative root 5, negative 2. And then it was root 5, and -2. So the opposite of x divided by y, give you a decimal approximation for that in a second. The opposite of x divided by y is also going to be this, which will be the same thing. The opposite of x divided by y will be that, which will be the same thing, opposite sign. So it's 1.12, -1.12, -1.12 approximately. I'll show you what that might look like on a graph. Do my best here. Math with bad drawings. Maybe I won't show you. All right, let's just pretend that that's a circle. So up here, somewhere there's a tangent line, and down here in this quadrant, which is symmetric across the origin, will be the same point, a parallel tangent line there. That's going to be this one that's in quadrant 1 and this one that's in quadrant 3. Right here are these two lines that both had negative slope. Then I have one that's in quadrant 4 here. It's like this. That is going to be going in a positive direction, and it would have the same slope as the one that was across from it here in quadrant 2, but we didn't find that one. All right. So we can also do higher order derivatives here implicitly. When we do so, we need to keep track of our previous derivatives. I do admit that prime notation is usually easier for this than having a whole bunch of dy, dx's, or dot notation will be equivalent. So let's go ahead and let's take this problem that we just did right up here, and let's find the second derivative for it, knowing that we just found the first derivative, y prime, a second ago was equal to -y/x. I'm not going to make you find that again. Okay, we just did that a couple examples ago. So we're going to take the derivative of both sides now. So derivative with respect to x of dy dx equals derivative with respect to x of -y/x. So this is going to be d2y dx2, which is the same thing as writing a second derivative like that. If you prefer that notation. And that's going to be using the quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So y double prime is going to be -x times my derivative for y plus y over x squared. X's will cancel. Y double prime, negative negative is a positive. Like so. And that's how I would give my answer, so that we've gotten rid of all of the derivative symbols on the right hand side, and we only have x's and y's over there. so that if somebody gave us an ordered pair, we can just stick in the x and y coordinates and get our answer. So try to not leave any derivative symbols of any type over here. Now that we've seen how to differentiate implicitly, let's discuss why we are going to need to know this. The main reason is going to be for related rates, and this is going to be used in creating mathematical models. And typically these are word problems. Let's just talk about this one for a second. This one's going to be a little more spicy, let's say, a little more complicated because we have that k value involved here. So the flow of blood through a blood vessel can be given as F equals K R to the fourth. So K is a constant. F is equal to the blood flow. R is equal to the vessel radius. And F is directly related or directly proportional to R to the fourth. K is the constant of proportionality. So K will change based off of exactly which blood vessel we're talking about. But if we're always talking about that same blood vessel, then that K value will be the same all the time for all F and R values. So F and R are functions of time. Even though we don't see time anywhere in there. So we really have F of t is equal to K times R of t to the fourth. We just don't see it that way. So now we want to ask the question, are df dt, the flow rate, and dr dt related? Does the change in the radius of the blood vessel affect the flow rate, or does the change in flow rate affect the radius of the blood vessel? Well, yes, is going to be the answer, but let's prove it. So let's differentiate. F equals K R to the fourth with respect to t time, and find out. So derivative with respect to t of f is equal to derivative with respect to t of K R to the fourth. So derivative, so df dt is going to be K as a constant that just passes through. And then derivative of R with respect to t is 4R cubed times dr dt, and we have an equation for something called related rates. So the answer to our question was yes. So this is a flow rate, this is a rate of change in the radius of the blood vessel, and they are related through this equation right here. So df dt is equal to the change in blood flow over time, and dr dt is equal to the change in vessel radius over time. We could ask additional questions like are F, R, df dt, and dr dt measurable in real life? Yes, if I had any 3 of the 4 of those, I could find the other. I don't want to do that right now. That's going to take too much space, and it's going to get messy to solve for a k value that has a 4th root involved because of, well, R. If I solve for R, it's going to be the 4th root of something that has k in it. I just don't want to do that right now. I'm going to come back and do some supplemental examples for this from the book, and I will take care of that there. So I'm going to just stop and put a pin in it right here to say we've found the equation for the related rates. And if they gave us enough information to find k in the original, which means that we'd need both an F and an R to find k. And then if we had k and R, because of getting k in the original, and then they gave us either df dt or dr dt, whichever one they gave us, we could solve for the other one. But let's consider another type of problem here where we have a tree that's growing, and as the tree is growing vertically, the radius of the tree is also growing, and there's this relationship where h is equal to 15 r to the 2/3 that we've just discovered that. So we need an equation that relates two things, 2 or more things. And we need to define our variables. And know what units we're going to be using. And what units they are measured in. Always important in word problems to answer in terms of units. So in this case, h is equal to my height of a tree. Say tree height. And that's going to be in inches here. And the radius of the trunk of the tree, and that's also going to be in inches. So we're going to now find dh dt is equal to 15 times 2/3 r to the negative 1/3 times dr dt. Simplify here. dh dt is equal to 10 r to the negative 1/3 let's put this down here. Cube root of r times dr dt, like so. All right. Now we're going to find that expression relating dh dt and dr dt. We just found it by differentiating, and use any given info from the problem statement to solve for the desired quantity. Okay, so now we're going to just pretend that we went back to the original problem and that we had given information to us in our word problem that said we're interested in finding dh dt when dr dt is equal to 3/4 of an inch per year, and original r that we're looking at is 8 inches. So if r is 8 inches, we could find the original height if we wanted to, but that's not part of our formula down here. We don't have an h anywhere in this related rate, so we don't need to find h. If h was still down here somewhere, we would need to calculate h from our original function. So let's go ahead and let's plug in and say dh dt is going to be 10 over the cube root of 8 times dr dt is 3/4. So that's going to be 30 over 2 times 4 is going to give me dh dt is 15 over 4. Remember, h is measured in inches, t is measured in years. So that's going to be 3.75 inches per year. Let's assume x and y are differentiable functions of t. Let's find dx dt, given that x is 5, y is 12, and dy dt is 2. Our function that we're dealing with here is y squared minus x squared equals 119. You can plug in x and y here and figure out that that is true, that if I take 12 squared minus 5 squared, I get 119. So let's differentiate both sides to get our related rate. X and y are just numbers here. There are no units, so we don't have any variables to define here. We have 2y times dy dt minus 2x dx dt is equal to 0. And we want to find dx dt. So negative 2x dx dt. I'm going to isolate the term that has dx dt in it. Solve for it in terms of my other variables. So dx dt is going to be y over x times dy dt. And let's solve for that now with the given information. So dx dt is going to be 12 over 5 times 2 is 24 over 5. And if we wanted to make that into a decimal, that's the same thing as 4 4/5, which is 4 8/10. Now we're going to do the problem that requires geometry that we were talking about before. That's going to use the Pythagorean theorem. So I'm going to just draw a right triangle here for this problem. We assume that our ladder is against a wall that should be perpendicular with the ground. That's typically how most walls are made for houses, is that they're perpendicular with the ground. So we're assuming we have a right triangle here. We have a 15-foot ladder. This is constant and should not change. The bottom of the ladder is initially 10 feet away from the wall and is pushed towards the wall, so I'm losing X value at a rate of 1/4 of a foot per second. How fast is the top of the ladder moving up the wall? So we want dy dt, which is moving in this direction. So it should be positive. It's equal to what? 12 seconds after being pushed. All right, well, I need to find a function x of t here. I need to start at 10, and I need to subtract 1/4 times t. And that'll give me my new position after 12 seconds is 10 minus 1/4 times 12. X at 12 seconds is 10 minus 3 is 7. So I'm really interested in at t equals 12 seconds, X is going to be 7 feet. And then I can use the Pythagorean theorem if I want to. Actually, I need to here to say x squared plus y squared equals r squared. So 7 squared plus y squared is equal to 15 squared. Y squared plus 49 is equal to 225. Y squared is equal to 176. And y is equal to plus or minus root 176. But we don't want the negative. Since we're dealing with distances, we only want the positive. All right. So be careful to not just start jumping right into the problem and using x as 10. We get the wrong answer because we're being asked about what happened 12 seconds after, not in the initial observed conditions when we were 10 feet away. All right. Now that we have that, and we can differentiate x squared plus y squared equals 225, get 2x dx dt plus 2y dy dt is equal to 0. Solve for dy dt, so 2y dy dt equals negative 2x dx dt, and dy dt is equal to a negative x over y dx dt. So again, recall here, x is going to be 7, y is going to be root 176, and dx dt is going to be negative 1/4 foot per second. These are measured in feet. So that means that dy dt is going to be, and feet over feet will cancel. So this is going to be negative 7 over root 176 times a negative 1/4. And this is in feet per second. Negative times a negative will make a positive. This is about 0.1319 feet per second. Remember to answer your problem in a way that makes sense to your audience that you're trying to speak to. So if this person is dealing with a ladder and things, we're probably not going to want to answer in square roots. This is probably something they want to measure with an instrument that they have that's going to give place values that are decimals. If this were an engineer that we were talking to and we needed to be very exact and precise, giving the answer with square roots and pi and things like that would be okay, because precision would probably be absolutely necessary in certain applications. But in things like this, where we're talking about somebody putting a ladder up against their house, then we're going to want to give our answer back to a few decimal places. Hopefully the problem tells you how many decimal places to answer to. So the ladder is moving up the wall at a rate of 0.1319 feet per second at 12 seconds after being pushed towards the wall here. So that's it for this video. And that covered both of our topics on implicit differentiation and related rates. We're going to come back next time and talk about applications of the derivative to find minima and maxima of functions, extreme values in an interval, and maybe absolute extrema as well. All right, that's it for this video. See you for the next video.